Last time we started section 2.1, the title was the derivative in the tangent line problem. And we did a couple of examples of how to do the limit definition of derivative, which is our new favorite thing to do, right?
Oh, yeah.
Of course. And we did one where we actually had a value given to us at the beginning. The value was 1. We plugged it in for x at the beginning. We worked our way through. And then we did a second one, which was a little bit more difficult, but the reason it was difficult was not because of this. We actually used the x as a value in there. We didn't change it to the number 1 or anything else. The reason it was difficult is because we had this sort of a double fraction business going on. Everybody remember that? All right. So we're going to take a look at yet another example, a different type of one. So the first one we did over here was actually a polynomial, 6 minus x squared. This one's a rational function, 1 over x squared. And the next one we're going to do is a radical function, okay? And this one actually gives us the 0.11, but I actually think it's easier to do the problem without the 1, 1 plugged in, and we'll plug it in at the end, okay? So my suggestion as a general rule of thumb is even if you're given a problem like this one where I showed you we could put the number 1 in at the beginning, you could also just reserve the number 1 at the end and just deal with x's throughout. So I'm going to show you how that looks, and then when you're given the choice, you can choose which way to do it. But let me show you how it looks on this one. All right, so the directions on this one say to find an equation. Now that's different. We haven't done that part of the directions yet. So I'll have to come back to that in a minute. Find an equation of a tangent line to the graph. And then it says to use your calculator to actually verify that it seems like a reasonable answer. Okay? So I'll show you how to do that as well. The first part of this, though, in order to find an equation of a tangent line, a line, one form of a line, the one that we're going to most likely be using the most frequently, is y minus y1 equals m times x minus x1. Whoops, let me get x1 in there. Now, you're given the 0.11, which means they actually tell you at the beginning what y1 and x1 are. Okay? What you don't know, and what we have to find, is m, the slope. And the way we find the slope of a curve is by taking a derivative. So we're going to use the limit definition of derivative that we saw last time. And let me remind you what it was. It said f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so is everybody sort of back in the mode of what it was we were doing? Remember that definition? Yes, ma'am.
Can I use something other than h? Do I have to use h like on a test, or can I use like delta x?
You could use delta x. Your book actually, I think it might even use delta x. Different books do different things. Both are standard. The reason I don't tend to use delta x is because if you forget the delta, it looks like x. Right. And then all of a sudden we've got a notational sort of confusion. So that's the reason that I use h, but if you use delta x, it would be okay. Just be careful. Okay? All right, so here's what we've got. And if you'll remember, we talked about the fact that this f of x at the end is the easy part because it's actually the equation we were given. Okay? So I just get to replace that with, in this case, square root of x. And the other part's the parts where I have to work a little bit more for. So the limit as h approaches 0, that stays. The division by h stays. And at the end, I've got now square root of x. So it's this part here at the beginning that I have to figure out what it is based on the equation I was given and replacing the variable in that equation with x plus h. So what will f of x plus h look like for this problem? Right, square root of x plus h. Okay, so far so good. Okay, half the battle is getting all that set up because if you can't get it set up, then you're not going to be able to continue the problem very efficiently, right? Okay, so this is what we have. Now, we saw a problem on a test. You saw problems in the last section that looked something like this. They wanted you to find limits, but when you tried to plug the number in, you got a 0 over 0, and there were radicals involved. Do you remember what we did when we had that happen? Conjugate. It was all about the conjugate, and that's exactly what it's going to be about here as well. So the conjugate for this looks like the x plus h, and then it's plus the square root of x, like this. And if we do it to the numerator, of course, we have to do the same thing to the denominator. Just like that. Now, the denominator we're not really going to multiply out. That's usually an unhelpful exercise. We just leave it all sort of in factored form. But the numerator, we do want to multiply out. I mean, that's the whole purpose, is in simplifying that numerator. So here's my denominator. And then my numerator, again, the reason that I picked the values I did is because if I were to multiply the inside terms together and I were to multiply the outside terms together, they're exactly the same, but opposite signs. So they add to 0. So I don't actually have to do that step. That's the whole point of the conjugate being used. So I do need to multiply the first terms together. So what happens when I multiply square root of x plus h times square root of x plus h? I get x plus h. And what happens when I multiply the last terms together? That is the square root of x. Good, minus x, fabulous. And then beautiful things happen to the numerator. What beautiful thing happens? Yeah, this is a plus x and this is a minus x, so those cancel. And I'll take one more step. You might be able to go ahead and do it at this step if you'd already recognized it, but I'll do it in one more step just to be clear. I've got h on top. I've got this h at the beginning on bottom. That is a factor, right? It's multiplied by whatever else is there. So because you have factors, they can reduce because of the multiplication. This h divides out like that. Please be careful. That doesn't mean you do not have a numerator, correct?
Correct.
Yeah, your numerator's still there. It's the number 1. So I've got the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Can I plug h as equal to 0 in now? Yes, I can. And if I do that, I will end up getting 1 over the square root of x plus the square root of x, which looks an awful lot like 1 over 2 square roots of x.
And do you want us to keep the x on the bottom, or do you want to?
It's a good question. A couple of things on that. So generally speaking, when we have radicals that involve variables, like the variable is in the radical, we don't try to do any rationalizing, okay? So it's good to leave it like that. At least it's acceptable. There's no reason to change it. On this problem in particular, though, we're not actually using x in general. Remember, they gave us back up here a point, right? So we actually have a value for x. Now, we found here f prime of x, which is our slope, is equal to 1 over 2 square root x. So we can find then f prime of 1 by simply plugging 1 in for x. So if I plug 1 in for x, what do I get?
1/2.
Just 1/2, right? So the slope of my equation is in fact 1/2. And I can take the equation that I wrote up here at the top and I can fill in m equal to 1/2, y equal to 1, y1 equal to 1, and x1 equal to 1. And then I can simplify for y equals. So I have y minus 1 equals 1/2 times x minus 1. Okay, now why am I doing this extra step? I didn't do this in the last 2 problems. Yeah, the directions were slightly different. They actually asked me to find the equation of the tangent line. So I do have to go sort of one step further. So here I have 1/2 x minus 1/2. We'll add our 1. And I have y equals 1/2 x plus 1/2. Just like that. Yes, ma'am.
On that part, like where it takes to like 1 over 2 square root of x, did you plug in 0 for the h?
I did, yes. And that's why you see the limit went away. It's because we did actually let the be 0. Good question. Okay, so this is sort of part A. All of this work is part A. Part B is to grab your calculator and to check out what your calculator is going to show you. So if you can, grab it. If you can't, look at a neighbor's, or you'll see mine in a minute up here. What I want you to put in is I want you to put in the original equation, f of x equals square root of x, into y1. And I want you to put the equation that we just got for a tangent line into y2. Sure.
Why do we have that plus 1 under the minus 1?
I'm just moving it from this side to this side.
Okay.
So I was just adding it so I got y alone.
Okay.
And in general, like, it's not really any better of a form to get it as y equals, but it's more of a standard form. And it allows me to use the calculator to plug it in as well, so that's another reason why we would want to do it in particular for this problem.
If it doesn't specify that, you can leave it as the other, right?
You can, because if it says, like on this one, it just says find an equation, technically yes, that's true.
If it didn't say to graph.
Right, if it didn't say to graph, it wouldn't be wrong to leave it, you're right. Okay, so I'm going to put in square root of x here, And I'm going to put in 1/2. I'll put in 0.5 because it's easier. 0.5x plus 0.5. And your standard window is fine, except that because this is a square root graph, I'm just going to let my x minimum and y minimum be 0 because I can't get anything that's negative anyway. And I'll graph it. So this is my square root graph. And then this is my tangent graph. And you can see it is, if you zoom in even, it's even better. Here, I'll just make my window go a little bit smaller. Let me go from, I'll just go out to 3. That should be sufficient. That's better. So you can see this nice smooth y equal x squared, or square root of x, excuse me, curve. And you can see the tangent line cutting through right here. And getting very, very close right here. And then sort of bouncing back right off of it. So visually, it gives us confirmation that it seems like a reasonable choice. Okay, so my graph that I did didn't prove anything, but at least gives us sort of a sense that we didn't totally screw this up. Okay? Now, if this graph totally like cut through the graph, we would have screwed up.
Can
So
you go to your y equals?
yeah, absolutely.
Oh, okay.
Okay? Any other questions on this? Okay, so like if you were doing this on your piece of paper now, right, if this were on a quiz, if this were on a test, if this were on WebAssign, you would have to show that you drew the graph, right? So you just sketch this picture that you're seeing right here as carefully as you can, make it look reasonably, accurate, that you're actually getting something that looks reasonably good.
Is that for any time it says a graphing utility?
Yeah. Anytime it says using a graphing utility, in terms of showing me that you've used it, would be to just sketch the graph that your graphing utility is showing you.
Do we need to put anything extra down, like the window that we use?
Um,
For the X and Y?
Probably not. It wouldn't hurt anything if you did, but it really is just more of a sketch. Okay, so and this one's saying using the graphing utility to just verify it to make sure that it seems reasonable. So it's really more of a visual check step than it really is about like proving something. That'd be great. Yeah. Okay, a couple more things in this section before we're done with section 2.1. There are some locations where tangent lines do not exist. In particular, there are 3 locations where tangent lines do not exist. One of them is at discontinuities, and we've got a couple of different kinds of discontinuities. Can you tell me something that would make a function discontinuous? A hole is one of those. An asymptote's another one. And a jump. You guys got it good.
This is a location where derivatives do not exist.
Uh-huh.
So,
Ah. Yeah, tangent lines or derivatives here. Either one are going to work.
oh, are they?
Yes, good question. Mine says derivatives, my screen says tangent lines. Is that true?
Yep.
Okay. Synonymous for what we're talking about here. Yes, good question. Thank you. So discontinuities. So holes, jumps, and asymptotes. They're not going to exist at any of those locations. A sharp turn. Now, a sharp turn looks something like this. Okay, so you've got this sort of graph that if you take a look at it from the left-hand side and you were drawing tangent lines, the tangent lines would be very steep and getting steeper, right? And they would all of a sudden, at one specific point in time, change very drastically over here. Okay, so the sharp turns create problem spots. You usually get those with piecewise functions, right? So they're defined in absolute values. Is that what you said? Yeah. Those are the 2 places. A lot of times when you see absolute values involved, or you see functions defined where it's like this equation when x is greater than 0 and this equation where x is less than 0, those typically create problem spots for derivatives and tangent lines.
Why is that? Like,
Because a derivative has to actually be able to be defined at a specific point. So at that particular one point, what would you use? Would you use the tangent line that's very steep and positive or very steep and negative? And that's sort of the problem, is that there's not a continuous way of defining it.
okay.
It doesn't matter if it's like sine x, find derivative of that, it's like a little different derivative. You know, it's
Yeah.
like a tangent line.
Yeah, usually what we say in terms of tangent lines or derivatives is that we need something that's smooth and continuous.
Okay.
So the continuous took care of sort of this number 1. Smooth takes care of 2. Okay? On number 2, we're not going to have a smooth graph if it's got a sharp turn, because it's got this sort of a rigidness to it. Okay. The third one's the weird one that like never happens, but I want you to be aware of it. This says a vertical tangent line. So a vertical tangent line, technically you could say the tangent line maybe exists, but it doesn't have a derivative or a slope because it's vertical. So if you had a graph, and they do exist, we just don't encounter them very frequently, where it had a portion of the graph that was extremely vertical. If you were to draw a tangent line in here, the tangent line would be a vertical line. And the problem with a vertical line is it has no slope, or we usually say the slope's undefined. So if the slope's undefined, then the derivative would also be undefined.
They only work for non-functions.
For what?
For graphs that aren't functions.
They typically are functions. They simply have this one location in the middle, like this very dead center point that causes a problem. And so, yes, if you didn't have a function, right, you had a lot of this, like, my pictures are almost over-exaggerated because it really looks like there's a vertical location on my graph itself. But these graphs typically don't have a vertical piece of the graph. There's just one point in the middle, where the derivative has this sort of a weird problem. As far as I can remember, I don't think we encounter any equations of functions that do this in Calc 1. But it is sort of an actual problem spot. It just doesn't occur frequently. Okay?
Why on the sharp turn is it just on a horizontal line?
Because a tangent line should be something that you're getting closer and closer to. Remember when we talked about our limit? We should be able to take these two particular points and get closer and closer and closer. And the problem is that if you did that over here and you got closer and closer and closer and closer, you're not getting close to a horizontal line. That's the problem. But if you had something that was smooth, right, it would be getting closer to a horizontal line as you approach that peak. You guys are asking great questions. Any others? Okay. Differentiability implies continuity. If a function is differentiable, that means it has a derivative everywhere, then it's going to be continuous everywhere. If it has a derivative at a specific point, then it's going to be continuous at that specific point. And the reason is exactly because it doesn't have those problems that we just discussed on that previous slide. Okay? In order for it to have had a derivative, it had to have been continuous. It's sort of the default, right? In order for me to be a mom, I have to be a woman. It's just a reality, guys. I know, shocker. Okay, so same thing. In order for it to have a derivative, it had to be continuous. So if I know it's got a derivative, I know it is continuous. That's all that this theorem says.
Is that going to be on the test?
This theorem might be. the mom and the child thing and woman thing, not probably so. All right, one more example. So this one has exactly a problem that we just mentioned on the previous 2 slides before slide, right? We've got absolute values, yeah? All right, so it says to describe the x values at which f is differentiable. Now, when things are talking about being this is differentiable, it usually means we look for the places where it isn't, and then we define it the other way. All right, we do that for continuity too, right? On your first test, what you really looked for when I said, if I were to have said where is it continuous, is you really would have looked for where it was discontinuous. All right, so if you take a look at this graph, I'm going to show you how to put this in your calculator because I think it's kind of cool. And then we'll talk about why the graph of your calculator makes sense that it would be this way. I was actually showing my son how to put this in the calculator the other day, the absolute value graph, because it's not maybe what you would expect it to look like in your calculator. So clear out what's in there. Okay. Are we good? Yeah, it does kind of look like Batman, doesn't it? Somebody's already got it on their calculator. Okay. There is a function that tells it to put those absolute value symbols in there. On your cool calculators that are like way more recent than mine, it probably even looks like absolute values. Does yours? Yeah. Yeah, mine doesn't. So if you've got an older version, it's going to look like mine. If you hit the math key, I think it's under math. Yeah.
Yep.
Yeah. Okay, so if you hit math, over here under num, N-U-M, the first one says ABS, like absolute value. Okay? So on my screen, it just says absolute value. If you've got the cool math type, it probably put those vertical bars in for you. And then you're going to put what's in there next. So mine's x squared minus 9. I'm going to close my parenthesis. If yours put the automatic bars in, then you don't have to close anything. And then just do a zoom 6. It's your standard zooming window. It looks something like this.
Yes, sir.
Do you see some sharp turns?
Yes.
Yes. Can you tell where they are from the graph?
Negative 3, 3.
Negative 3 and 3. And the reason is that if you were to have graphed this without the absolute values,
You're gonna pull.
Those are X's.
whoops, what was it? Yeah, x squared minus 9 graph. I would have had this graph. So what the absolute value graph did is it took the part that's beneath the x-axis and what did it do? It flipped it up because that's what it was supposed to do. It was supposed to take everything that was negative and made it positive. So that's what's happening. So the location where we've had these discontinuities are exactly where it's hitting the y-axis. I'm sorry, excuse me, x-axis, I meant to say. All right, so if you're taking a look then at the question in your or on the screen over here, the places where we actually hit the x-axis are the places where this is going to equal 0. So x squared minus 9 equals 0 are going to be my sort of problem spots. And this factors as a perfect difference of squares. So x minus 3 and x plus 3. So x equals 3 is going to be a problem spot, and x equals negative 3. So it's going to be discontinuous here. That's not the right word. It's going to be non-differentiable is what I want to say. I can't find a derivative here. So the question actually asks, where is it differentiable? And it's going to be differentiable everywhere else. So there's lots of ways to write that. The one that I think that's most common is to write it sort of going from left to right, negative infinity, all the way until you get to negative 3. We do a union from negative 3 to 3.
Is that a U or a B? We're gonna
It's-
do some website.
It's a U, and I think that it will require you to do it on WebAssign, yeah. And then there's a U, and then I've got 3 to infinity. And let me talk about the notation in case you haven't seen it or haven't seen it recently to remember what it is.
And that
Could
would
we
domain.
use, could we use an
Do you have
inequality?
If WebAssign lets you, that's fine. And if you want to, for me, it's fine too.
Yeah,
The
the ones
problem
I-
is the inequalities are going to be messier looking, probably.
The ones I've done on WebAssign, like there's multiple choice ones, and it says where is the graph differentiable, it uses inequalities.
It does use inequalities.
Yeah.
So if you were to use inequalities on this, it would be where x is less than negative 3. Negative 3 is less than, x is less than 3, and x is greater than 3. Those would be the inequality statements.
Do we have
So-
to define which is domain or range or?
These are all domain values because they're all x values.
Okay.
Mhm.
Okay.
Okay, so this notation is sort of moving from left to right in terms of your graph. The graph's left-hand side is negative infinity. X values is what I'm talking about. And you've got all the x values until you get to negative 3. And then there's a spot where you have to break. So the parentheses mean I can't equal a value. So you see a parenthesis next to the negative 3. U means union. It means sort of like joining with something else. So like think about like a marriage union. You join all your stuff together. You're joining the different parts of the graph together. So then I've got negative 3 to 3. Again, parentheses because I can't equal them. And then I've got another union, and then I'm joining from 3 to infinity after that. So that's how that's read. Either of those notations is fine with me. I don't care which one you use. So, all right. Any questions on this question? All right.